Okay, so this little zero, of course, means standard states, which is 1 molar or 1 atmosphere pressure. Now, to generalize it to just delta G without the zero, okay, which is what they mean by non-standard. Non-standard is this delta G without the zero. Okay, that's what that is, non-standard. So there's a formula basically, and the formula is related to not having 1 molar concentrations or 1 atmosphere pressure. So to understand the formula, there's a version of K that's known as a thermodynamic equilibrium constant. And there's also a version of Q that's a thermodynamic Q. So they're not really, I don't think they're very clear here on the fact that in this formula, you have to make sure you're dealing with the thermodynamic Q. Okay, so this is this is the formula we're talking about to give the non-standard delta G. This is what that is. In order to use that formula, we first calculate standard delta G, which we just talked about doing in the last section. There's 2 ways to do it, depending on the temperature. But then you also need this thing here, the Q. Remember that Q is a reaction quotient. Reaction quotient. That's what the letter Q stands for, quotient. Reaction quotient. This Q, though, is a little different in general from the reaction quotients we've already talked about. So who can tell me reaction quotient Q that's equal to the concentration of products over concentration of reactants. Right, just like K is.
It's at equilibrium.
What'd you say?
It's at equilibrium.
K would be at equilibrium. What's Q though? How does Q differ from the?
Yeah, that's at initial.
Right, initial value. So these concentrations would have the little zero, not the zero for standard states. This meaning initial, or you could put an I there for initial. That's what Q refers to. So that means when you start a reaction, you could calculate the Q based on reactants and products, initial values. So let's say we started a reaction and there were no products. What would Q be equal to at the beginning? The top part was 0.
0.
Q would be 0, right?
0.
So Q starts at 0 if you don't have any products, and then it gets bigger as you go along. And we know that we reach equilibrium at the point when Q is equal to what?
K.
K. Yeah, Q becomes the value of K when you reach equilibrium. All right, so that's what we're talking about here with the reaction quotient. What's different, though, a little bit different, is that this particular Q is a thermodynamic reaction quotient. Sorry, I have to write so slow. And the thermodynamic reaction quotient is defined a little differently, because for reactions that only have solutions, aqueous solutions, or any other kind of solutions where you have concentration, thermodynamic is the same as what we all talked about. So for solutions, we use concentration. But now, if we had a reaction that involved gases, previous sections in the previous chapters, could we still use concentrations if we had a gas mixture instead of a liquid solution? Yeah, you could. Sure, we could put molarities for gases in there too. You can't do that with the thermodynamic Q or the thermodynamic K. If they're gases, you have to represent the amount of the gas as a pressure. So in the thermodynamic Q and the thermodynamic K, solutions still use concentrations, but anytime there's a gas, gases use pressure. And the units of the pressure are atmospheres, just by convention, which kind of doesn't make sense because atmosphere isn't actually even a SI unit, but that's the unit that's used for any numbers that you're going to see in this in this chapter. So if we have a reaction that has both gases and aqueous solutions in them, you're going to have a mixture of units. You're going to have molarities in there, and you're going to have atmosphere pressure in that expression. So that's something to just to be aware of. Now, if a reaction only has gases, then you'll only have pressures. So what would the thermodynamic K be the same as for something that only has gases? What did we already see that used partial pressures only? There was another name we gave for a K that has only pressures in it. What's the subscript we put on the K in that chapter 16? If you were using partial pressures instead of molarities.
P.
P, yeah. So K sub P with a subscript P, that's the same. So K sub P is a thermodynamic K. Thermodynamic K. For the same thing, because you can only have K sub P if all of the reactants and products are gases. And for that case, then you're following the restriction for thermodynamic K, and where you have to have gases being in atmospheres. And since there are no aqueous components, if you can do a K sub P, you can't have an aqueous component in there. So that would make it always the same as K. K sub P's are always the same as thermodynamic K. The case with subscript C, though, isn't always the same as the thermodynamic K. There would be a difference if there's both gases and aqueous. And also, if you have gases in there, you can't have a thermodynamic then they do another calculation with the same reaction, vaporization of water, when you're not at equilibrium, which is this here. So if you're on a particularly humid day, then you have a different partial pressure of water. If you put that in there, then you're not at equilibrium because you're showing that, or I guess this is, let's see. Yeah, this is still room temperature. Oh, a non-humid day. Okay, so yeah, that makes more sense. So here they're saying if the humidity is low, let's say it's this value here. Still at room temperature, still at the same temperature as they had in the previous problem. But now, if your humidity is low, that means the air is not saturated with water vapor. There's not an equilibrium established between the water vapor and the air. So you're not at standard conditions. And so if you plug that value in here for Q, and you do this whole calculation putting R and T in there. By the way, the R has to be the energy unit R, 8.314. This is 25 degrees still. Then you work it all out and you come out with a non-zero value for delta G. When delta G is not zero, that means you're not at equilibrium. The important thing about this non-zero value is that it's negative. Okay, so if I'm looking at a delta G that's negative, what does that say about the process that they're considering here? The process of H2O liquid going to or in equilibrium with the vapor. If my delta G is negative, and that meaning that I'm not at equilibrium, then which ways does this thing have to shift to move toward equilibrium? Forward. Right? Got to shift forward. So that's going to shift forward until it reaches equilibrium. Now, what does shifting forward mean for water? Liquid water. What's liquid water doing when this reaction shifts forward?
Becoming gas.
Is what?
Becoming a gas.
Becoming a gas. What's another word for that? More common word for water becoming a gas? Evaporating, right. So water's evaporating. So they're saying this is a non-humid day. Does it make sense that water would evaporate on a non-humid day?
Yeah.
Yeah. That's why it makes sense that we're coming out with a negative delta G zero. I'm sorry, negative delta G. So that's what they're doing there in that example is just kind of showing you an example and also showing that it makes sense that you're getting that particular value for the delta G in that situation. But in general, you could calculate the free energy change for any chemical reaction where the reactants and product are not all at 1 atmosphere or 1 molar concentration. Okay, I'm going to stop there, and I haven't quite wrapped up the chapter, so there's not that much left to do.